Hello. Today we're going to talk about Topic 4, Section 7, Discrete Random Variables. So a probability distribution is all of the outcomes in an experiment. So think about rolling dice. It would be rolling a 1, a 2, a 3, a 4, a 5, and 6. Okay, that's all the outcomes. Flipping a coin, heads, tails. Okay? Now, all of the individual probabilities must be between 0 and 1. Right? The odds of rolling a 1 on a die is 1 out of 6. The odds of flipping and getting a coin and flipping and getting a heads is 1/2. All right? Now, the sum of all those probabilities must equal 1, right? Flipping a coin and getting a head is 1/2. Getting a tail is 1/2. 1/2 plus 1/2 is 1. All right? That's the rules that have to be true, okay? It is easy to mess that up. It is easy to get weird calculations with negative probabilities or probabilities that are greater than 1, right? I always convert it to a percentage, okay? A percentage is always between 0 and 1. 0%, 100%. You aren't going to say there's a negative 50% chance. That sounds ridiculous. And you are never going to say there's a 150% chance. Well, that's more than 100% chance. That means 100% means it's going to happen for sure. More than sure doesn't make sense. Okay, not in the world of math. Okay, so watch out. Don't get weird values like that. Probabilities have to be between 0 and 1. Now, exam tip. If you get the wrong probability, so let's say you get 1/3 and the answer was actually 1/6, you can still get full marks, okay? I'm sorry, you can still get your partial marks or whatever if you continue with that with your wrong probability, as long as you interpret it correctly, okay? They won't give you partial if you have weird probabilities. Like if you say a negative or a 1.05 probability, right, more than 100%, makes no sense, right? They throw it out. They say you don't know what you're talking about. Okay, remember that a discrete random variable is one that you can count. Okay, these are your examples. We use them for the binomial distribution, geometric distribution, and the Poisson distribution. All right, here's an example, right? We talked about flipping a coin. Okay, so here we're going to just record the number of heads after we flip a coin 3 times. So this is your sample space, all the different chances, okay, all the different outcomes that you could have, okay, in order. And X is going to denote the number of heads. Well, the number of heads we can get is 0, 1, 2, or 3. So what's the probability we get 2 heads? Look at our options. Right? We have head, head, tails, head, tails, heads, and tail, heads, heads. Where did I have that? right next to each other. All right, so that's 1 out of 8 possibilities, 1 out of 8, 1 out of 8. Okay, so that's us writing it all out. Okay, that's not so hard because it's 3 coins, or 3 flips. Okay, here's the probability distribution. We can count them up and see that it looks like this. Okay. Now, a continuous random variable is the outcome of experiments that involve measurements, right? So, height and whatnot, when you can get a bunch of different possibilities. This would be like using your normal distribution, exponential, the gamma distribution, and the chi-square distribution. That's when you use normal or continuous random variables. Okay, so here's our first example of a probability distribution. So we are finding how many of the 5 targets at each station the competitor has missed. So missing 0 targets, 1 target, 2 targets, 3, and 4. They have misplaced the data for missing 3. They can still collect it because the probability distribution says that if I add up every single outcome, then my total should be 1. Okay, that's the trick we wanted to know here. All right, we combine like terms, we get, what is that, 0.8? So then we get k equals 0.2. So the probability of missing 3 targets is 20%. Okay, so here's another example. All right, so don't be thrown off by all the variables. Okay, notice it says for when I is these different numbers. So let's focus on when I is 1. Okay, so that means x equals 1. That would be k over 2 times 1. When I plug in 2, that would be k over 2 times 2. Plug in 3, k over 2 times 3. And hopefully we're starting to see a pattern. Okay, so I plugged in every value of I, and that is the probability distribution for each value. Those are the only i's that it can be. So I have to add these all up, and that should equal 1. Okay, so let's see. In Cognity, they got all the same denominator of 120. The numerators all added up become 147k. So k equals 120 over 147, which simplifies to 40 over 49. So here it just represents a constant. So we can plug that back in, and then by plugging in i's, we will get the actual probability for each one of those occurring. Okay, so remember, k is just a constant. Okay, so expected outcome is helpful when you're playing a game, right? You want to know what the outcome is going to be, you know, whether it's worth it to play the game or not, right? A fair game is when the payout is 0 for both players, right? Nobody has an advantage or disadvantage, or at least it would be equal, right? So to get that expected value, what you would want to know what would happen in a game, okay, if everything occurred, right, and on average, you would take the x value times the probability of that happening, and then you would add it up for each of those values. Okay, it's much easier to do with an example. Okay, so here's our first example. So these are the outcomes: 0, 1, 2, 3, 4. Okay, think of it like doing a scratch-off ticket, right? Getting $0 back, $1 back, $2, $3, $4 back. The probability of each one, right? That would be great if it was that much. Okay, the expected outcome of that lottery ticket, okay, we would do the x value, so the outcome there would be 0, times the probability, so 0.25, maybe I should use parentheses, all right, plus the expected outcome for 1, so 1 times 0.15, plus 2 times 0.15, plus 3 times 0.2, plus 4 times 0.25. Okay, we know that the probabilities equal 1, but now we want to know what the expected outcome is. Okay, so this becomes 0 plus 0.15 plus 0.3 plus 0.6 plus 1. All right, which is 2.05. So this scratch off would have a payout of $2.05. So if they don't want to lose money, that scratch off ticket should probably cost more than $2. Okay, at least $2.05 for them to make any kind of profit. Okay, because that's what they're expected to pay. Okay, hopefully that makes sense. All right, here we have another example. So we have two players using a 20-sided die. So notice dice isn't always 6-sided. All right, we assume that it's all equal probability. It's not weighted. So if player A rolls a prime number, they win 5 points. Otherwise, player B wins K points. So we either have player A wins, okay, or we have player A loses. Oh, I was about to say loose. Loses. All right, so this happens when a prime is rolled, and this is not prime. Well, think about what a prime number is. Hopefully you know what that is. It is your 2, 3, let's see, 5, 7, 11, 13, 17, 19. Okay, so we have 8 options out of 20-sided die. So not prime would be the other 12 numbers. Okay, so that is the probability. Ooh, almost spelled that really bad. Okay, so think of our little chart here. It's really bad, sorry. And then we have the payout. Okay, so don't be confused with the payouts here. So player A wins, they win 5 points. If player A loses, that means B wins the points. Okay, and that difference is what you're looking for, right? You're wanting X represents how many points player A is winning by, right? You know, points are, the more points you have, the more you win, right? Or not the more you win, you win. So they would, player A, this would affect them negatively. Okay, so think about you're affecting the same person. Don't put plus K because that doesn't, A is not getting points here. Okay, so the expected outcome is you would add these values together and that would tell you the difference. Okay, so we would do 5 times 8 over 20, and then we would do negative K times 12 over 20. Okay, that would be the expected outcome. Okay. Well, oh, I should probably make that look more capitalized. Okay, the overall expected outcome is, multiply those together, add them up, and that should equal 0 because we want to make it a fair game. Okay, so that's what we're trying to do here. So 2 minus 3k over 5, right, once you simplify everything, equals 0. So you get k equals 10 over 3. Okay, so that's the payout, all right, which is a little over 3 points. Okay. Okay, so why don't you try this one? Pause it, see how you do. Find E of x. Okay, so you do the payout times the probability. And we want to know, is it fair? So we want to see what that equals. Okay, we're trying to figure out what does it equal. Okay, fair means it has to equal 0. So let's figure this out. Yes, this game is fair. The expected value is 0. So that was one question. And yes, game is fair. There you go. And I don't like how I did that circle, of course. So let's start another example. So why don't you pause it, see what you can do. All right, so the first thing I would do is the probability distribution. So 0.2 plus p plus q plus 0.2 must equal 1. So p plus q must equal 0.6. All right, then we can also do the expected value. So 1 times 0.2 plus 2 times p plus 3 times q plus 4 times 0.2 must equal 2.5. So 2p plus 3q, once you solve that, equals 1.5. So now it's just a system of equations. You can use your calculator, substitution, elimination, graphing, whatever. Okay, when you solve that, you get B. Okay. All right, last slide. What you should know. Okay, so this is what you should know by the end of this topic. If you have any questions, please ask me in class. Please don't hesitate. Again, I can't stress it enough. If you don't understand it, you can't interpret it, you're nowhere. Okay? So ask away. I know it's kind of fuzzy sometimes.